So you remember yesterday we were working on the Hardy-Weinberg? So I'm going to start. You know how yesterday's we did two or three questions, I think. So I'm going to show you an example of a question that is, because you always start simple and then you always try to make it a little bit more complicated, right? So I'm going to show you an example where we could use the Hardy-Weinberg to study an allele and look at how it changes over time, which is what?
Evolution.
Right. Microevolution, the frequency of an allele changing over time. So what do you think would happen to an allele if it caused disease that made you sterile? Do you expect that allele to increase in frequency or decrease in frequency? Decrease. So imagine we have an allele Q. It's recessive, and if you have one copy, you're fine. But if you have two copies, you can't have babies, okay? So, easy enough? Easy enough so far? Okay. So, if I have 1,000 individuals and 100 are sterile, what's the frequency of that Q allele? So, if you recall yesterday, the Hardy-Weinberg, we always use the, what? Dominant or recessive phenotype? Right. And the recessive phenotype is Q squared. And in this case, Q squared would be 100 that are sterile. Or it's always over the total, right? So it's 100 that are sterile. And how many individuals are there? 1,000. So what would Q be in this case? What would Q be? What do you think? What do you think Q would be? So we do the square root, right? The square root of 100 over 1,000, which is the square root of 0.1, which is like 0.3 something. What is it? I can't remember what it is. 0.3. What's square root on it? Sabrina, what is it?
0.316.
So I'll just say 0.32. Okay? And that means that P, which is a dominant allele, has to be 0.68, because remember, those two have to add up to what? To 1. Okay? Now, so in this generation, the frequency of my Q allele is 32%, and the frequency of my P allele is 68%. Now, microevolution means small change. What would you expect the numbers to be in the next generation? So, your prediction should be that Q should go what? Should go down. Why? Why will Q go down? You can't pass on the alleles, right? Okay. So, who can have kids?
Guys.
Who can have kids?
Circuit? Girls.
In this scenario, who can have kids? If you're Q squared, so remember there are 3 genotypes. P squared, 2PQ, and Q squared. Okay. So they can have babies, but they cannot. Now, so in this population, we have 900 individuals, right? How many can have babies? Sorry, we have 1,000 individuals. Sorry, what I meant to say was, of the 1,000 individuals, only 900 can have babies, right? But what we need to do now is we need to figure out, okay, how many alleles are there? Because we have 900 individuals. We know that these two have to add up to 900. Because we're told that 100 are Q squared. The problem is we don't know of the 900 how many are P squared and how many are heterozygous. But we could figure it out easily. Because we know now what P is, right? So what we could do is we could say, alright, well, let's figure out what P squared is. P squared would be 0.68 squared. So what would that be?
0.46.
So in other words, 46%, right? And what would 2PQ be? Well, that would be 2 times P times Q. So what would that be? Should be like 0.44 around. So we'll just say 0.44, because we already know that, well, this is 46%, that's 44%, that's 90%. And that's the amount of population that can breed, right? 90%. 900 out of 1,000 can breed, because 10% can in this case. So what we could do is we could say, oh, okay, well, we know then that of our population, because our population is 1,000 big, right? 46% are p squared, so that would be 460 what? Individuals. And 44% are heterozygous, so that would represent 440 individuals. So there's our 900 now. We know the makeup. We know now. Look, this is statistics, right? Is it exactly 460 and 440? Maybe not, but this is a prediction, and it's probably going to be pretty close to that. So 460 individuals are predicted to be p squared. 440 are predicted to be 2pq. We know that these guys cannot contribute alleles. So the only ones who can contribute into the next generation are these guys, or these individuals. I shouldn't say guys, these individuals. 900 individuals would have how many alleles between them? How many alleles would 900 individuals hold? It would be 900 individuals times 2 alleles each per individual. Oops, whoa, what happened there? 2 alleles. That would be 1,800 alleles. Right? Only 1,800 alleles are going to be represented because, remember, 100 individuals can't reproduce. So we lose 200 alleles in this population. We're done. Can't get to the next generation. So now we're going to figure out, okay, what's the frequency of P and what's the frequency of Q? We know that there are 1,800 alleles that can get to the next generation. So we know it's going to be out of 1,800. How many P alleles are there? Well, you saw yesterday that an individual that's P squared has how many P alleles? How many alleles would a P squared individual have? Well, P squared means PP, right? So that's 2 P alleles. So this individual over here would have 2 alleles. So that would be 920 P alleles from the P squared. But where else is the P allele? In a heterozygote. How many P alleles does a heterozygous have? 1. So that would represent another 440. So that would be a total of 1,360 P alleles. So that's my P, 1,360. My Q is only represented here, and that would be 440, because 440 individuals each have 1 Q allele, so that's 440 Q alleles. Those two add up to 1,800. So now what we could do is we could figure out what's the proportion of P and what's the proportion of Q. So what would that be? So what's P's allele? Now this is for the next generation, okay? Because we already know what P is for this generation. We know it's 0.68. Well, what is it for the next generation? So what's 1,360 over 1,800? 0.7, we'll just say 0.76. Therefore, this will be 0.24. And Sabrina, you predicted that the P allele would go up, right? And the Q allele will go down. And that's what the math tells us. Okay? So here's another example of using the Hardy-Weinberg. But this one is a little bit trickier because in the previous examples, we didn't really take into account the fitness of the allele. We said that the P and Q allele were equal. Like there was no difference between the P and Q allele. Well, guess what we're going to start talking about? What if there is a difference? Okay? And here's a neat little example of that. It's still the Hardy-Weinberg. I didn't use any different math. Okay? But here's just another example. Now, I have questions for you in the course outline, and I will show you no, actually not in the course outline. In a document, I will show you later where they are. Okay? Alright, so, questions about Hardy-Weinberg? Yeah.
Yeah, we have a question real quick before you take other people's questions. This isn't about this.
Alright. Okay, so that's the math. Now, remember how we talked about for the math to work, there are 5 assumptions you have to make it. You have to assume to make the math kind of work. 5 assumptions were these ones. So here's the thing. Let's imagine we're monitoring the numbers. In the previous example that I gave you, right? This question here. Which of those 5 assumptions do you think would explain why it's not in equilibrium? Because if something is in equilibrium, the math would say that this is the P allele in this generation, and it should be the same in every generation. If something's in equilibrium, it means it doesn't what? Doesn't change. But you just saw there that it did change. It went from a p-value to a higher p-value, and the q-value went down. So if it's changing, we have to think about why it's changing. And here are the 5 reasons. And they're actually, you're going to see what the 5 reasons what they are, because remember this is the assumptions that we use to make the math work, right? We assume no mutation, no migration, population's big, population has random mating, and there's no natural selection. Which of the 5 do you think is being violated in that example? Right. Because in that case, there is an advantage to being one allele, or having one allele. Which allele gives you the advantage? P or Q? P. Because if you have Q allele, you have 2 copies, you're at a major disadvantage because you're sterile. You can't have babies. So let's talk about if you are looking at an allele or a gene that has 2 alleles and their alleles are changing, why are they changing? Because if they're changing, that could indicate there's evolution going on. Now we got to try to figure out why is it changing. Okay? And what's the cause? So in this scenario here, here's another example. Maybe Q squared is 4% one year. Maybe the following year, it's 15%. It's changed. 15% is much different than 4%. So what's the reason? Okay? It's not in equilibrium. So look at the potential causes. You'll notice that they're the same as the assumptions. Maybe there's a new mutation. Maybe there's gene flow. Maybe there's drift. Now, I'll explain what drift is. Because drift has to do with population size. Remember, in the assumption, we have to assume the population is really what? Really big. So, this has to do with population size. Maybe the mating is not random, which means it's assortative, or maybe there's natural selection going on. Okay? So this is what we're going to look at right now. But we have another question from the peanut gallery. Okay, so let's take a look at these things that can affect the frequencies. Alright? One is mutation. Now, do you guys know what a mutation is? Okay, what is a mutation? Angeli, what is it? What's a mutation? Change in the what? Okay. Why would a mutation change the why would mutations affect the Hardy-Weinberg equilibrium? But what? And hey, by the way, this is just some information about mutations. You know, they can be good, but mostly they're going to be bad or neutral. Okay? And we'll talk a little bit more about that later on. The one I just showed you, the mutation that caused the Q allele to make you sterile, that would be what? That would be bad. The mutation that gives you the allele for cystic fibrosis, is that good or bad? You'll see maybe not so bad. Yeah. You'll see maybe not so bad. The allele that gives you sickle cell anemia, the allele, I'm not saying the disease, the allele that gives you sickle cell. Remember, an allele is 1 copy, right? The disease is when you have, if it's recessive, 2 copies. What about the allele that gives you sickle cell? Good or bad? What do you think? Nah, it's green is like, I don't know what to say anymore. What do you think? You gotta wait. The allele that gives you sickle cell, good or bad? Well, you'll see, it depends. It depends. It's going to depend on the environment. If you have 2 copies, it ain't good. But I'll show you later on in this unit, 1 copy may actually be good. Okay? Depending on where you are, though. To think about mutations, mutations give you new alleles. The equation only accounts for 2 alleles, P and Q. If you get a mutation that produces another allele called, what's the letter after P, Q? Okay, we'll say P, Q, and R. Can P plus Q equal 1 if you have R now? No. So a new mutations will produce new alleles, which will throw the allele frequencies out of whack. There's no more equilibrium now, because now you have new alleles. So that's one. Second one is gene flow. This has to do with populations moving in and out. So I'm going to give you an example. Blonde allele. Let's say that there is an allele that gives you blonde hair color. Now, hair color is probably polygenic. I think it's polygenic. At least the human baby face lab made you think it was polygenic, right? Let's assume it's simple, that is 1 gene. Okay? There's a blonde allele. Now, imagine that blonde allele is 3% in our population. And we have 1,000 people. And then, all of a sudden, we have 400 people show up from Sweden. What happens to our blonde allele? It goes up. Because if you look at Sweden, what do you notice? They have a lot of blonde people. So that population has a really high frequency of the blonde allele, right? What will that do to the frequency of your allele, the blonde allele in your population, if they come into your population? Increase it. Increase it, right? So when populations move, it changes allele frequencies. Okay? So that's one thing that we have to remember. One of the assumptions of the Hardy-Weinberg was what? No migration. What's the opposite of no migration? Migration. Gene flow. That's called gene flow. Okay? A third one is genetic drift. Now, this has to do with the third assumption. What was the third assumption again? The third assumption was populations are really big. Now, this has to do with population size. Okay? Drift is randomness. Random fluctuations. If I said to you, okay, I want each of you to flip 10 coins, what do you think you'll get?
50-50.
That's what you predict, right? But do you think everyone in here is going to get 5 heads and 5 tails?
No, I'm guessing 75 heads, because I always think of it.
But if you did that experiment, we would get, because you're only flipping the coin 10 times, right? You could get really drastic results. You could get 5 and 5, you can get 6 and 4, you can get 7 and 3, you can get 8 and 2.
You can get 10 and up?
You could. It becomes harder to get 10, but it's possible. But what would happen if I said, okay, I want everybody to flip a coin 1,000,000 times? So, if I said to you, let's flip it 1,000,000 times, do you think anyone in here would get 80% heads? What do you think? Remember, you're flipping it 1,000,000 times, not 10 times. 1,000,000 times.
Probably. I don't think our cost to do it.
What do you think? Yeah, it's almost impossible. Okay? The idea is this. When numbers get bigger, they become, you should be able to predict them more accurately. Right? Like if I have 2 kids, right? Statistics says one should be a boy, one should be what? Right, half and half. But, you can easily get 2 boys. It's 25%. That's a pretty big number. If I said to you, there's 25% chance of you dying if you leave this room, you ain't leaving the room. 25% is a big number. But, if I give you 1,000,000 kids, you should expect that no one would produce 1,000,000 boys. It's almost impossible. Right? Because as numbers get bigger, the the randomness. It's almost like it's less random, more predictable. Okay, and that's what this has to deal with. So drift is randomness, random fluctuation. So, give you an example. I can start off with a population of flowers in generation 1 here. Now, this is a very small population.
So are you recording this?
Yeah, why? Am I recording it? Yes, I am. This population initially has how many plants? How many do you see here? 10? There's 10 plants here, right? Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The red allele here is 70%. But because the population is so small, that it's not unreasonable to think that the red allele could randomly fluctuate to 100%. It's very possible. It's harder, though, if the population is much bigger. So when populations are small, you can experience these really random fluctuations. Just like with coin tosses. Same idea. Now, I'm going to show you something that has to do with drift called bottlenecking. Now, do you know what a bottleneck is? Yeah, so what happens, if you visualize a bottleneck, it's like you have a bottle, and then as you go up the bottle, the diameter of the neck is what?
Decrease.
Okay, it decreases, right? So it kind of looks like this. Okay. So let's imagine we have a random chance event, because drift is all about randomness, okay? Random chance event that maybe we're population on an island, okay? Volcano explodes. And 90% of the population gets wiped out. And it had nothing to do with your fitness, okay? Because sometimes you can be more fit than someone else, you're just wrong place, wrong time, okay? 90% gets wiped out. Random chance event. Your surviving population is much smaller. Obviously, you have 1,000 individuals, 90% get wiped out, you're left with 100 individuals. Here you can see it visually. You start with a population. There's some catastrophic event. Could be a major drought. Could be a landslide, ice age, maybe an asteroid hits, okay, earthquake, volcanic eruption, and you're left with a small population. Now, here's the thing. Look at this small population, and I want you to compare it to the original population. There's no yellow. So what happened here? Randomly, the yellow got eliminated. But also, something else happened too. Randomly, what happened to the blue versus the white? See, what happened was the blue allele and the white allele was probably, I can't really count it, but it looks like it's pretty even. And then here it ain't even anymore, right? It's 5-1. So it's 83% blue and 16% or 17% white. So populations can experience these random fluctuations. When populations are small, the randomness is more of a factor. So sometimes the alleles are changing and has nothing to do with natural selection. It's just randomness. So here's an example of alleles, okay? And what you do is you start off with 2 alleles at this point right over here, 2 alleles that are 50-50, and you run a computer simulation to see, well, what happened randomly to the alleles. You'll notice something interesting. They never stay like this. They never stay flat. If they stayed in equilibrium, you would expect it would always be 50-50. Okay? What happens is they start to diverge. One starts to increase, and as one goes up, the other one must go, because they have to add up to what? To 1. But that's when the population is small. When the population is bigger, what do you see? You actually see the same pattern, but it's just not as dramatic. So the idea is, as populations get smaller, randomness will affect the allele frequencies more. There's more fluctuation. Okay? Now, one thing that, as you just pointed out, when you have a random chance event that wipes out population, you just notice something. You notice that yellow got eliminated. So I'm going to ask you a very simple question. What does bottlenecking do to variety? Yeah, it decreases it. Okay. So how would you know if a population experienced a bottleneck? Beautiful. Say that again? If you looked at a gene, you notice that there's hardly any variation at that gene. So the individuals are almost identical to each other. Not that they're not identical, but they're very similar. Okay? So if you look at like cheetahs or the northern elephant seal or even us, we are, remember the number, we're like over 99.9% identical. Why? Because elephant seals, cheetahs, and humans experienced a severe bottleneck. Now, what happens in that case? You can see from the visual, you lose variety because everyone will be descended from a very small population. So you're going to be really related to each other. More so than if you came from a bigger population. So I got a trivia question for you. Imagine your job was to go around the world to figure out what is the oldest indigenous group on this planet. The oldest group of humans. Humans, not fish. So, do you know what an indigenous population is? It's a population that's been in an area for a very long time. Okay? So, where would you find this? How would you go about finding this indigenous population? But how would you find it? What would you look for? It has to do with what we just talked about. Think about the reverse logic. What would you expect the oldest population to have more of? Right. More variety. In this case, what's the new population? This one or this one? It's this one. What happens, if you think about it, the original population has to have the most variety in it. Because every other population that came from that group would have to be smaller. Because we talked about bottlenecking, but the same thing is true for something called the founder effect. Now, the founder effect is when you have a group of people that leave, they take off somewhere, and they go to start a new colony. Right? It's the exact same idea. If you have a small group that leaves, so the difference between the two, in bottlenecking, there's some catastrophic event that eliminates virtually everybody except for a small group. Founder effect, you have a small group that leaves. But the idea is still simple. That small group has to have less variety than the original group. So if you want to know what the oldest group is, that probably all other groups came from, you would have to look at the group with the most variety. And Lauren, where do you find that group? In Africa. Okay? Because that's where humanity evolved. In Africa. So that's what you would expect to find this group. Okay, so here's an example. So, do you notice something wrong with this, I guess it's a baby. Yeah, its fingers are deformed. So this is a symptom of a condition called Ellis-Van Creveld syndrome. It's a form of dwarfism. Okay, in addition to short stature, you see this other symptom. Okay? Trivia question, what do you call it when a gene produces multiple symptoms? Very good. Pleiotropy. Okay. The frequency of this allele is, in the normal population, is 0.001. So that's 0.1%. The frequency of this allele in the Amish population is 70 times higher. So it's 7%. Why? Why do you think it's so much higher in the Amish population than in the regular population? Well, based on what we just talked about, why do you think it's that? Yeah. So how would you explain it using this model? Because the Amish population would have come from an original group, right? So how would you explain it using this? So let's imagine that what color then would represent that syndrome?
Yellow.
It would be yellow, because the allele for that Ellis-Van Creveld syndrome is very rare, right? What is it? It was 0.001. So it's very rare. So we could say that it's the yellow allele, right? Now look, in this case, we got blue and white, but is it possible that you could have gotten a lot of yellow? So what would have happened then in that case where the surviving population did not have blue and white, it had actually quite a bit of yellow? Or in this case, it's not really the surviving population, it's the founder population. So maybe there's some yellow in there. So maybe we have quite a bit of yellow. Now, what happens when they go off, form a new colony? What happens to that yellow allele? It's more prevalent, and therefore it will be passed on more likely, right? Because it's more prevalent. So there's two explanations for why this allele is high. One, maybe it was just high because when the original group broke off, maybe that allele frequency was just randomly high to begin with. Or, what's the other explanation? Because the group is small, maybe the allele randomly increased in frequency. Okay? So the big idea is when populations are small, you can expect some random fluctuations where the numbers are really different, but again, it's just due to randomness. Nothing to do with natural selection, nothing to do with sexual selection, just random chance event, the number was higher because of a founder effect or bottlenecking or just drift, randomness of the alleles going up and down. Okay? I'm just going to explain one last one and I'm going to end it, okay? So almost done. The fourth assumption was mating is what? Yep. So if your allele frequencies are changing, another possibility other than randomness, other than gene flow, other than new mutations, is sexual selection or assortative mating. So here's a picture of a pretty ugly fish. It's called a stickleback. Now this is a mosaic version. So it's got a little bit of different colors. It's got some red, some blue-green in it. A melanic version is all uniform color. So you wouldn't see the different colors that you see in this fish. Females that are melanic like males that are melanic. Females that are mosaic like males that are mosaic. That's the opposite of randomness. Because if it was random, then a female wouldn't care what the male looked like. So when you see something like this,
It's a bunny, chicken, bird, and squirrel.
how many of you ever seen a ridiculous male peacock?
I love peacock.
No, it's not. It's not a peacock. But how many of you ever seen a ridiculous male peacock? You ever seen peacock? They're ridiculous. Okay, a male peacock is absolutely a ridiculous animal. Here, watch. Let's go to YouTube. Male peacock. Okay, so here's a male peacock. Look at it. This is one absolutely ridiculous animal. Think about this. Look at this poor guy, okay? He's brightly colored. Okay? He's got this massive tail. That's kind of cute, right? And he's got to do all of this. He's got to display. Look at it. Look at this. Look at this. Think about Hubbard. No, hold on a second. He doesn't have any bodyguards. Doesn't go to school. There are no laws in his world for killing peacocks. He's not protected. It's ridiculous when you think about it. Look how much attention he's dragging to himself. Think about this. Think about this for a second, okay? This is not human. We don't really have any natural predators we got to worry about. Yeah, we hear stories that humans get killed, but that's accidental. This thing, who lives in the wild, has to worry about nasty cats and things that don't want to eat it. This male peacock is prancing around with his massive tail, making lots of noise, very brightly colored. What the hell is that doing? Is that? No, the female's smart. The female doesn't even look like this. The female is very bland, very boring. Okay, in birds, it's the males that are beautiful. Okay? In humans, it's debatable. Damn, I'm being recorded. Okay, anyway. So, look, when you see something like this, you automatically know that this bird does not look like it could even beat up the Easter Bunny. It doesn't really have much going for it. Okay, it would lose many fights. So why is it doing this? I mean, if you
want the girl.
Right.
Am I right?
Of course. Courtship. Now, so if an animal is willing to risk its life to attract a girl, now think about this. Hold on. Can the mating be random?
Yes.
Imagine that hold on a second. Imagine that a female peacock didn't care about males and just mated randomly. Would you see this? No. Because then there would be no benefit to doing this. So when you see ridiculousness like this, okay, then that's telling you that that the type of reproduction that you're seeing is not random. It's the opposite. There's sexual selection going on here. Well, same thing. The problem now, this is not as ridiculous as the peacock, but you still got this very bright coloration. Look, this bird almost perfectly blends in, except for this thing that sticks out. I think it's a pheasant. I don't really know. Maybe it's a roadrunner? I don't know. Bitty, that's all, folks. Okay. I think it's a pheasant. Or a roadrunner. I can't remember. I didn't get my PhD in ornithology, so I didn't. Anyways, okay, so next time we will talk about natural selection. The fifth assumption.
Okay.
All right?
The end.
The